My name is Toma Iwato. I'm a graduate student at Doshisha University. Today, I would like to talk about our study influences on stiffness and weather direction of rubber belt and frictional coefficient of between the belt and pulleys on shifting properties of CVT. At first, I would like to talk about the background of our study. This picture shows continuously variable transmission, CVT. CVT consists of V-grooved pulleys and a rubber belt. In these pulleys are slide in the actual direction, and the bigger widths in change. Therefore, winding pitch radius of the belt is changed, and smooth shifting is possible. From the viewpoint of coefficient of friction, usage of rubber belt is effective to transmit the power by relatively low pulley thrust force. It can be downsizing and weight saving of CVT units. On the other hand, comparing the other type of CVT belt that made from steel, this stiffness of rubber belt is comparably lower. Therefore, the deformation of belt during operation when specifications of the belt were changed should be investigated in detail for designing the optimal rubber belt. However, there are few studies that focused on the deformation of rubber belt during operation. So, the objective of this study is to investigate the effect of the frictional coefficient between the belt and the strips and stiffness and width direction of the belt performance of CVT unit, such as the thrust tension conversion ratio. At first, I would like to talk about the belt used in the test. We used three types of testing belts. This illustration shows our testing belts. These belts consist of fabric top layer, cord, wire, and compound rubber. In this study, the elastic modulus and width direction and frictional coefficient were changed independently in each belt. This slide shows our testing system. This illustration shows the testing system used in the investigation. The power generated by the AC motor was transmitted in from the driving shaft to the thermal shaft through the CVT unit. Next slide shows measurement of thrust tension conversion ratio. This is the testing conditions of the maximum examination. This diagram is the example shows change of the speed ratio. Speed ratio of the CVT was changed constantly by being moved a shape and of the driving pulley during shifting changing. Then, change of total thrust and the interaction force were measured as shown in these graphs. The thrust tension conversion ratio during shifting up was calculated by this equation using values of the total thrust and the interaction force. Next slide shows the test results of thrust tension conversion ratio. Relationship between the frictional coefficient and thrust tension conversion ratio is expressed in this diagram. On the other hand, the elastic modulus and width direction of the belt and the ratio is expressed in right side. It can be seen that Thrust tension conversion ratio was increased when frictional coefficient or elastic modulus in width direction of belt were increased, regardless of change of the initial thrust. Therefore, we consider the mechanism of change of the ratio by changing the elastic modulus in width direction of the belt. We thought it this way. It means winding radius of the belt and pulley groove will decrease by occurring of deformation in width direction of the belt when thrust applied. Then, deformation and decrements of belts of one belt can be thought to expressed in this way. From the results of calculation by using each equation, radial decrements was decreased when elastic modulus of the belt was increased as written here. As a result, tension on belt will be sought to increase by increasing elongation of the belt when the elastic modulus in width direction of the belt is high. Now, we confirm changing radius of the belt and pulley group by using two-dimensional laser displacement sensor. These diagrams show the winding radius of each belt shifting up and during shifting up and shifting down. When the condition of speed ratio was 1.00. And then the belt winding radius was calculated, being considered curvature deformation on the belt back. Now, I would like to talk about the results of the measurements of the belt winding radius. In this slide, relationship between belt winding radius and elastic modulus in width direction of the belt are shown in these graphs during shifting up and down. As a result, we can find that belt winding radius is suddenly increased when elastic modulus of the belt is increased, regardless the change of shifting condition. In conclusion, it will find the tension was increased by increasing elongation of the belt when elastic modulus in width direction of the belt was increased due to winding radius of it was increased. Then finally, thrust tension conversion ratio was increased. I would like to show conclusions of our studies. Thrust tension conversion ratio was increased when frictional coefficient or elastic modulus in width direction of belt were increased. Accurate radius of belt winding, which cannot be estimated by theory, can be calculated being considered curvature deformation on back of belt. Increasing elastic modulus of belt in width direction was effective to keep the thrust tension conversion ratio high. This work was financially supported by Bando Chemical Industries. We expect a lot of thanks here. Thank you.